So the idea is now to use the Bernoulli formula, the Poiseuille's formulation that we had developed before on this system. Now what we have here is, this is a geometry for which we had already simulated the airflow. And under the simulation, so this was the allometric target, as in, think about the formula that I just shared with you guys. So this was a male subject. So the first one, 2.72 W to the power of 0.44. The body weight of the person is given as 94.5. So if the body weight, so let me write it down, given weight of the adult male is 94.5 kg weight. Can you just do a quick calculation to check how much the Q would be if it is 94.5 is W? Because I want to double check if that was indeed that allometric target and see if it's that user. How much? 20.1. 20 point? Yeah, so I'm right. So this is what we had. So we ran the CFD simulation 20 point, targeting the flow at 20.13 liters per minute. What we achieved was slightly different. We achieved around 20 liters per minute, and that 20 liters per minute was developed under a pressure gradient of 7.78 pascals. So that's the CFD difference. A pressure drop of 7.78 pascals led to a flow rate of 20 liters per minute. Now let's see if we do use this theoretical formulation for the same pressure drop, what kind of flow rate could be generated in a geometry like this. And just a slide, it's not a correction, rather a clarification that the derivation that we just did, thanks to it, that it is, you can think of it as something as a straight line as well. Either way, the mathematics doesn't really differ at all, because we are eventually going to see the fluid molecule traversing this delta C. That curvature, if you think back on the formulation, that curvature never plays in the derivation. So this is basically equivalent to a straight path. This picture that I have here, I have included that just to show what is the model system that I am thinking of in the problem, but you can also think of it as a straight linear pipe. Doesn't matter, because we are claiming that this is the delta Z that the fluid will traverse. And this is given to us as 130 mm or 0.13 meters, and that dimension is an approximate of what the dimension was in the real subject from here to here. Okay, so let's look at the other. So this is the figure. This would be clearer in your printout. So this is the CT scan of the same subject. So this is a sample tomography, computer tomography slice. And to extract the airspace or the airway from this scan, again, I think on your printouts you can see that the whiter parts, they are actually the bony structures. The gray parts, they are the tissues, and then the black ones are the air spaces. So you can see that on the very edge, the black of the outside air matches with the black of the respiratory airspace. So that is dependent on the corresponding radio density value for that region in the picture. So the airway radio density range is between negative 300 to negative 1024 Hounsfield units. You can look up what is Hounsfield unit, but basically it is This is the ratio of the different optical refractive indices in this kind of systems. Now, negative 300 to negative 1024, that helps in the case of, I think someone was asking yesterday what kind of tool we use to segment and develop this kind of airspace geometries. There are some open source softwares like Slicer 3D which you can use. We typically use something called Mimics. And be it Slicer 3D or Mimics, you can directly input that this is the radio density range that I want to extract. And that would give you the very first iteration of the geometry. That won't be very useful straight go. So basically you need to then go back into each of the scans. So as I said, it's a collection of different slices collected at different penetrative depths through the head. You look at each scan. After that default thresholding of negative 300 to negative 1024, you have to manually correct the pixels. Sometimes it will pick pixels that are not really part of the airspace. Sometimes it will leave out pixels that should be included in the airspace. And you also need to make sure that the transition from slice 1 to slice 2 is smooth enough. So it cannot be like this. So that's all done typically in collaboration with the doctors, and that's what was done for this person as well. And for that matter, when we get overtly excited, we don't only take the airspace. So over here, we also use the radio density values for the face to generate the face of the person. We just need to make sure that the eyes are closed to make sure that it is de-identified. And you cannot recognize the person from this. Okay, so this is the radio density range value, negative 300 to 801024. The software just for record keeping for this course was Mimics that was used to get this 3D models. So to segment the scans. Okay. Now from here we are trying to get or basically apply what we might get from the reduced from the theoretical model and see how different the values could be compared to the full-scale CFD results that we have already over here. So this is the reduced model for theoretical analysis. Now over here the mean size, let's assume it to be 1 centimeters, and we are moving from A to B. Assume the delta P A to B to be same as the pressure that could achieve the target 20 liters per minute airflow in the 3D CFD case. So we are going to apply a pressure drop of negative 7.78 pascals. We have already verified that was the first question. If you look at your lecture notes, I first have the students verify the 20.13 liters per minute, the allometric breathing rate. So that was the first question. So in terms of questions, verify the allometric target for the breathing rate. Which we already did. The second question is compare the inhalation airflow rates using theoretical formulation and the given numerical results. And the third part on the lecture notes that we have is explain the difference. And by now we know why there should be differences, because the pipe streamline flow is missing all the details of the flow features that are formed in the form of the secondary flow patterns. But let's basically do part B, which is figure out the inhalation flow rate for the idealized model. So part B, delta P is negative 7.78 pascals. And we are trying to generate Q, which is minus pi R4 over 8 mu delta P delta Z. All these parameters are given to us. So minus pi, the radius is 0.01 meters. So 0.01 to the power of 4 by 8. The mu is not given to us, so let's write it down. So mu, we can use the same value that we have been using, but what I have on the lecture notes is 1.825 times 10 to the power of minus 5 Newton second per meter square. And that is right. Now this mu air, by the way, is the viscosity coefficient for inhaled warmed up air. So if you typically look up on the internet the value for viscosity for air, it is slightly different to the values that we use. And you are right. This is by 2. This is the radius that we're talking about. So 8 times 1.825 times 10 to the power of minus 5, and then delta P is negative 7.78, and delta Z is this 130 millimeters, so 0.13 meter. Can you give me what the Q value is? Huh? That's not at all what I have, so could you double check? Second? Am I doing something wrong, or this is also not the value that I have? 8, yeah, that is what I have. Second, 8 point? 8.044 10 to the power minus 9. No, minus 4. Minus 4, yeah. So I have 8.05 times 10 to the power of minus 4. What is the unit here? Meter cube per second. Sometimes when I teach, this is, by the way, this is not new material. I teach this as part of a course called Engineering Mechanics in Biomedical Applications at SDSU. So I have done this problem. This is the 7th time that I am solving this problem. So I make the students, because some of them are undergraduates, do the dimension check and make sure that the units are correct. I'm not going to make you guys do that. In your class, you follow the SI system. I do. They have hired me, so they need to follow my units. So they in the US versus they put all these FPS systems. I'm tired of that, so I don't even go into that direction because I am going to confuse myself. So meter cube per second, but we have to convert this to liters per minute. So do that. So basically you have to multiply by 60 and then 1000 for the conversion. 48, yeah. So 48 liters per minute. So basically you see that the pressure drop of negative 7.78 pascals, which generated a flow of 20 liters per minute in the full scale 3D, generated a much faster flow of 48 liters per minute. And it makes sense in hindsight, right? Because in the anatomical model, it has to go through all these topological deformations, all the vortices that are creating that negative pressure, stopping the flow. It has to overcome all those things. And over here, the same pressure drop does not have to counter any of those flow field artifacts. You can directly push the flow through the pipe. And as a result, the Q is almost double the magnitude. So as a result, it doesn't really make sense to idealize a flow field because we are not going to get the results correct. On the other hand, what we were doing before in the particle transport analysis, we already fixed the velocity value of the field. So once we fix the velocity value, the drag was more or less what would have been in the real case. But here is something else. Here we are using the pressure drop to generate the flow, and the field value changes. And it is not tenable. Does it make sense what I'm trying to say?
Force for the decrease in the vertical because it is trapped somewhere.
So think about what is going on if the topology is complex. The flow is swirling, let's say, and that is creating some kind of backflow, right? And that is creating some trapping, some barrier towards achieving its full potential.
The unidirectionality is lost.
Yeah. So let me write that down now. So from the theoretical idealization, we have Q as 48 liters per minute. In full scale anatomical CFD, we have Q as 20 liters per minute for SEM delta P. Why is that? So the CFD results are lower, or the full scale results are lower because number one, the recirculating airflow in the anatomical appendages is absent in the theoretical model. So if we were indeed trying to keep the same flow rate, so if we want to generate a 48 liters per minute flow rate in the anatomical model, we have to apply a stronger pressure drop to push that through. And number two, the vortex patches in the anatomical, in the physiological field create localized low pressure, let me borrow your terminology, low pressure traps that can slow the flow down. Or the Bernoulli's principle lovers might have issues with that particular statement. Pressure is low, then velocity is very high. That's what they understand, right? So let's not use that. So the low pressure traps that can create local barriers to the overall flux. Okay. Again, just to repeat, while trying to explore the particle transport, we did not have to worry about that because there we were fixing the flow rate, we were fixing the V fluid to make sure that the drag is realistic. Here we don't have that benefit anymore, and hence idealization does not work if we are trying to understand the fluid dynamics of the respiratory tract. It works if you are trying to set a final exam question for your undergraduate students. Then it works. Then you can let them solve this. They are happy that they can apply Virgil's law, and then still they don't get the answers correct. So then they are not happy. Okay, so the last thing for today would be to just introduce some elements of CFD, which hopefully we would be able to do some of tomorrow. many of you have? I know I already asked this question, but can you just remind me how many of you have run simulations? Uh, you have. You have. Anyone else? What kind of simulations have you run? Runs in systems. In what kind of system? But what is your geometry? What problem?
Swirl actually. There is a sentimental only the swirl is
I
and
see.
then we need to study the house of fertilizer to pass through the swirls. And then we calculate the pressure and velocity.
So one thing it can be done, if you have actually done analysis, maybe you form subgroups. What do you think?
Yeah,
So
yeah.
that like you can divide yourself into 3, 4 together, and then the guy who has done actual analysis can take the interested in the.
So you can probably lead a team of like 3 or 4.
You, Parimal, Rahul, and who else has done analysis? In case he has done analysis, he is now switched to the open form.
Okay.
And he has like basic ideas.
So you know them better. What their skill level.
Yeah, yeah. So anyway, you all among yourself organize into 3, 4 groups, and then maybe in the cat lab, they can sit together or in your laptop, whatever is the most.
So the plan for tomorrow is we are not done yet, and I still need to write some. But the plan for tomorrow is I would first like to run the simulation myself, but basically launch the simulation how it should be done, so that you have a first-hand knowledge of how it is supposed to be set up. And but I have already have the simulation files on that the .dat files on the folder. We can directly use that to do the polymer tracking. But let's first finish up for today. So computational fluid dynamics. So people who raised your hands, do you guys use commercial packages or are you developing in-house codes? Commercial. And you are
actually Ram did some course in MATLAB also.
in MATLAB. Okay, okay. And someone you are doing open form. Okay. You are doing open form, right? Yes, sir. Right. Okay. So, by the way, one aside comment: the drop impact simulation that my student ran, I think he has used OpenFOAM as well because he is also learning OpenFOAM. So we just need to clarify that with him. Okay, so computational fluid dynamics. So we know that it is entirely based on the kind of spatial discretization. Like it starts from some level of spatial discretization. So the different kinds of spatial discretization techniques. Do they have any kind of CFD codes here at the graduate level?
Most of them are graduates.
Okay, okay. So
Mechanical, we offer him MTech as well as his students of the tech.
okay. So you know this very basics. So finite difference technique.
Chemical, Chinese side doesn't offer CFD course.
So maybe graduation not in place.
Okay, but in MTech, maybe they haven't done, but in chemical MTech also they offer.
Okay, 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 okay. So in terms of the discretization methods, we know we have the finite difference technique, and the finite volume technique, and the finite element method. Now, in terms of the work that we are going to do, and it seems like people who have run numerical simulations, we are using commercial packages. So let me write down some common ones that people use or we are using. So ANSYS Fluent is something that I use in my group a lot, And then we have console, open form, star CCM. Star CCM is, by the way, very popular amongst some of the other fluids guys in my department at SGSU. And abacus. So each of them, they use different kinds of discretization. So for example, Fluent is based on FVM, console is finite element method, and then OpenFOAM is FVM again, and then the other two are FEM. So in terms of the workflow that we are going to follow, I'm not going to get into the details of CFD in this course. That was not the idea. So I'm not going to get into these methods. Rather, let's quickly discuss the different steps that we are going to follow in the work that we are going to do. So number one, digitize the geometry. So by this I mean that you get the scans, the computer tomography CT scans, they come in a certain file format called DICOM files, and then you extract the airspace on each slice and then you stitch them together. Thankfully, we are not going to do that in this course. We are going to use models that have already been built, because just building that, digitizing that geometry anatomically would need input from the clinicians. The geometry is built already. After that, we will be developing the mesh. So mesh or grid, the geometry. And in your lecture notes, you will find that I have added the protocols for meshing. If they're not included in the lecture notes, then go to that cloud folder. I have a separate folder for protocols. So the meshing protocol is there. For ANSYS, the other package that I wrote, ANSYS ICEM, that's where we are going to do the meshing. Number three, we will simulate the inhaled flow field, the inhaled airflow field. So again, this is a decoupled system in the sense that we don't run particle as, so we don't run the simulations as a two-phase simulation. So if we had, then the particles would have impacted the momentum of the field around it. We don't. We first simulate the inhaled airflow field because the particles are considered tiny enough compared to the length scale of the flow. And then we do particle tracking. So this is Lagrangian tracking with inert particles. The method that we use on Fluent is GPM, discrete particle method. By the way, there will be some, so if you are noting this down, there will be a correction in the lecture notes because this particular phrase I picked it directly from the course that I teach, and we don't do particle tracking in that course. I just ended the flow field simulation. So after the flow field, we do particle tracking. So this is Lagrangian inert DPM tracking. And finally, we will do post-processing. So we will track some particle sizes, figure out how much of those particles are going to land at a particular site in the airway, and then we are going to go back to some research papers, similar to what we did with the theoretical work. So we derived some formulations. We eventually got to a point where we can use the formulation to derive what the particle transport trends are like, and that formulation was found to be in a paper that was published last year. We are going to do the same thing with the CFD work. We are going to run a simulation, do the particle tracking, and then compare our numbers with something that has been published. So in terms of the papers that you should look up tonight would be this. So if you go to on the cloud folder, if you go there, look up this particular paper, two papers. So this is this one. So Basu, this is my paper, Basu Scientific Reports 2020. And then the first one, Akash 2023, Frontiers in Drug Delivery. So both are papers from my group. The 2020 paper was when I was still new as a faculty, and this 2023 paper was led by my PhD student. Do a quick read through because I think I'm eventually going to show some results derived in class here and found in both these papers. And of course, the 2023 one is a little bit more updated in terms of its techniques. So let's stop here. So we are going to start with simulation tomorrow.
So we may meet tomorrow in the meeting at 9.